Hello everyone, welcome to Lab10's initial video, and in this lab we are designing a very simple CPU. And as you probably remember, in Lab9 we started designing very simple CPU, and we have actually given you the initial design, which had ADI and no add and BZJI implemented in Lab10 and Lab9, and we wanted you guys to implement ADI and BZJ, and then also CP and CP lowercase I. So that was 6 operations done, and in Lab 10 we are requiring you guys to complete the rest of the instruction set, which has 10 operations. So in this lab you're going to complete all 10 operations, and let's read part 1. And in part 1, you're just going to download the instruction set folder and then re-familiarize yourself with the set. And as you can see here, these are the files that you need to have a look and comprehend. And as you can see here, you can see the opcodes of each instruction and the immediate flags as well and what they do. And if that is sort of short, you can always check here to make sure what you're doing is correct. And then for part 2 in this lab, you're going to start on the design, and then once you complete it, you're going to synthesize and simulate it. And you need to see that simulation has no errors. It should say simulation successfully done, or something similar to that. And then the synthesis also should have no errors or warnings except the trivial ones, which are delay warnings, or more than 100% of device resources are used. Or you might also have a multiplication warning, but we will get to that when we synthesize our code on Xilinx. And let's see. In this part, you're going to download these files, which are in Verilog TV folder, as you can see here, and you need to go and download these files, and you need to add them on a Xilinx project for Lab 10. Add these ones, and then you need to also put this file in the projects folder so that it can automatically be included. And then you're going to have in your initial design BZJI and add, and then we need you guys to copy the code you have from Lab 9 and then add them to this CPU design, so you can continue working on the rest of the instructions, because you also need ADI, BZJ, CP, and CPI as well, so you can take them from Lab 9. And let's see. Okay, our test assembly code is being run in the test bench, so that test should pass for you to successfully finish your lab. And the PDF is pretty much done, so I don't really need to have anything else to mention, except you just need to submit only the simple CPU.v file, and ignore this one. I'm going to correct this one later on. And you just need to submit the very simple CPU design you have. And let's have a look at the files now, the files that we've uploaded. And as you can see here, we have our CPU design, which has the BZJI and add operations implemented, just like in Lab 9 initial video. And you can just replace the design you have from Lab 9 to Lab 9 with this, so you can continue working on the rest of the instructions. Or you can just add the lines you have added again here, and then go on from there. And let's see the test assembly we have. Okay, as you can see here, it tests almost all of the instructions. Let me see: CP, CPI, CPI, CPII, BZJ, BZJ, mul, muli, add, addi, adti, lt, nand, nandi, SRL, SRLI. I think it tests every instruction, and you don't really need to do anything about this assembly code. This assembly code is already turned into machine code for the test bench, and it is in this file here. These 32-bit values are the corresponding machine code for each of these instructions. And after we can go on, after this we can go on to the test bench. And as you can see here, we have some tests being done here and here as well. There are I think 33 tests, so you need to make sure all of these tests pass. And if there is some sort of an unexpected thing that happens, it will display this line, and you can correct it accordingly. You can get a verbose output to understand at what nanoseconds the error occurs and which opcode, which operand A and B are cared about for this instruction. So you will solve your designs easily. And also there may be some errors, and they will also be printed out. But otherwise, your test benches should say simulation successfully completed, or if it has failed, it will say this or both of these. So if you have these ones, you need to correct your designs. And just to remember, you need to click on Run All button to complete your test bench in this lab. So that's a warning that I am doing right now, but I will also show you it when we get to the Zidings part. And also we have here our simple CPU design calling and our memory. And just a quick look into the memory file. We have our basic pins, our basic signals, and then our inputs and outputs. And we have here the writing logic and the reading logic. Basically, this is the output, the data out, and it outputs the address inside the memory, the address you've given inside memory, and it also writes to that memory into the address if the write enable signal is high. And that's basically what it is. And it also calls the program.v file. It includes it automatically, so you don't have to include it in your design on Xilinx. So that's about it. And I think you are already familiar with the simple CPU design. So we can just get to the Xilinx part after this one. So let's see what we do from here. Okay, for the Xilinx part, I have already implemented the simple CPU core, and let's synthesize it, and let me show you the warnings that should be coming up, but otherwise you shouldn't have any other warnings. Let's synthesize the code. As you can see here, I'm on implementation, and I've already set this as the top module, and it has synthesized, and in the console it does synthesize is completed successfully. There is no errors. However, there are some warnings, and as you can see here, it should say delay is ignored for synthesis about 5 times, and it should also say this one to warn us about these warnings. And it should also have, you guys should also have this warning as well. And okay, these ones here are also fine. You don't need to care about these ones for lab 10. as you can see here, it does say if you are doing this on purpose, you may ignore this warning, so it is fine. And here, as you can see, this is also a possible warning, so it should be fine. You don't really need to get rid of these warnings, so it is fine. And now let's test our design using the test bench. Let me click on test bench and then click on simulate behavioral model. And let me also click on run all button, which is this play button right here, to completely finish my test bench. And as you can see here, it did finish our test bench. And here it does say simulation successfully completed. So let's check the waveform now. And to be able to do that, as you can see here, I can't even see my clock period. So I'm going to be clicking on this magnifier with the minus sign to be able to see my clock period. And as you can see here, it does show my period fully. And let me make it shorter so I can debug it easily. And also, just a reminder, you can also add some more signals to this window, and you can also delete some signals from here, just like this. And let me click on delete to delete these ones, since we don't really need them, since they are just parameters. And as you can see here in the instance and processes name window, you can just choose the memory or the simple CPU to add some variables from this to the window. So let's add, for example, maybe p counter. However, p counter is here, so maybe let's add opcode, operand 1 and 2. Let's add num1, num2, and also state, which is pretty important for this design. And let's just relaunch our code so that these new signals are also added to the memory of this waveform. And as you can see here, we are relaunching our simulation. And let's also again click on the run all button, and our simulation does successfully complete. And let's see, also let's do the radix unsigned decimal, and let's check our design. As you can see here, do I have my test assembly code? Okay, let's have it like this here, and let's do this one. Okay, here the reset button goes to 0, so state 0, as you can see here, this during this time our state is 0, but then in the next cycle our state becomes 1, and it reads the CPU design wants to read 101 address, which is the A address, and it should read 18 here, as you can see it does. And then it reads B, address B, which is 102 in state 2. And then since it reads that value, it should get 2. And as you can see here, it does get 2 in here. And since this is a CP instruction, it should write this 2 value to the memory in address 101 using write enable 1 in also state 3. As you can see here, this is all that happens. And also in state 0, we request to read the instruction, and it does read the instruction as this decimal value 2149138534, and it gets this value in state 1 normally. Since this was during reset, it stays as the first instruction being read. So in state 1, we get the result of read program counter, and in this state we divide this memory into its opcode operand A and operand B, and as you can see here, our operand 1B and opcode get the value in state 2, since we are using a flop to enter these numbers into opcode and operand 1 and operand 2. So you can, as long as you're in state 1, you can use opcode next, operand 1 next, operand 2 next, to check some stuff in your design. Like, let's say, when you're in state 1, I'm not going to go into the whole, let me actually also maybe write it in the CPU design so it's clearer. Here, since the operation, since the instruction is just being divided, it's being parsed, you can use opcode next in your if statements, or also in your, for example, right hand side of the equal sign assign operation. So that is also fine to do for this state, since they are just being parsed. But otherwise, you should use just opcode, and also here not the next value, the normal value. So that's how it should work for you. This also goes for your projects as well. And let's get back to the design. It does write 2 to 101, and after that, let's go a bit forward. The program counter becomes 1, and then it reads the instruction 1, which is this value 24176066661, which corresponds to CPI 103 and 5. So it reads 103 address, which is 12, and it reads 5, which is this random value, and it doesn't really matter since we are using CP lowercase I. We're going to just write 5 to this memory. So it writes 5 to 103 using write enable equals 1. So that's basically how it's all working. And also in SRL, for example, here it reads instruction 2, which is SRL 104 and 105, and then it reads 104, which is 65, 105, which is 3, and then since this is 3, it's going to shift the data, which is 65 by 3 to right, to 3 bits to the right. So 3 bits to the right, so it should become 8. Let's also check it again. 65, the value 65 should be something like 0, 0, 0, just leaving zeros, and then 1, 0, 0, 0, 0, 1, I think I might be missing a 0, 1, 2, 4, 8, 16, 32, yes, I am. 1, 2, 4, 8, 16, 32, 64, and 65. So we are shifting by 3 bits to the right, which means that let me copy these ones, which means we are going to delete these ones, and then we are going to add 3 bits here. So the new value becomes just 8. So it does write 8 to address 104. So that also works fine. And also let's just check, for example, a CPI operation, which should be in instruction 30. So our P counter should become 30. Let me go there using my arrow keys. You can use the left and right arrow keys to move between the changes in the signals, so it can be easier for you guys. Let me move there. And as you can see here, it does a BZJ or BZJI operation in 28 to jump to 30, which, as you can see here, it is a BZJI operation. And let's go and check CP capital I operation. And it reads here the instruction, which is at 30, which should be this value 268658291, and then it reads 137, which has 138 written there, and we need to also read that address since this CPI A B is star A star B. So if our instruction is CPI 136 137, we're going to write to 136, but then we're going to read 137, and as you can see here, we have read 137, and we have got 138 here, and that means we are going to also read address 137. So we are reading 137 as well here, and then we get 5, which should be changed like this. Let me show you. And as you can see here, this just says write 5 to address 136. So it does write 5 to address 136. So that's how it technically should work. You can have more than these for cycles. It should be fine. But if you can have just 4 cycles, it's kind of, I think, better, but it's not necessary. You can have more cycles for this instruction or any other instruction. It should be fine as long as it does work. And okay, in address 32, we get our go to end function, and after that the function itself stops. And I think that is largely due to line 34 in test bench here. And the test count is reached a specific number, it does finish. So that I think should be fine. Just make sure you can see simulation successfully completed here. And you should also probably check the waveforms here and maybe add some waveforms here, because these will be useful to debug your code for project CPU. And I think that's about it for this lab, and see you later.